Alright, DOT, Federal FAA Technical Center, Atlantic City International Airport, New Jersey 08405. De-icing of aircraft turbine engine inlets. H.A. Rosenthal, D.O. Nalsapaz, H.M. Rocket Holt, Roar Industries Incorporated, Chula Vista, California, June 1998. Final report. This document is available to the U.S. public throughout the National Technical Information Service, Springfield, Virginia. 22161 DTIC selected. Alright, executive summary, introduction, objectives, background, de-icing, technology status overview, anti-icing, de-icing, ice detection system, ice accretions of de-icing, evaluation, physical properties of ice, computer and analysis, ice and de-icing, worst case de-icing conditions, engine manufacturer icing experiences, safety requirements, substation, allowance of ice accretion, allowing ice ingestion, ice impact effects, ignited components, generally structural analysis, impact dynamic, safety issue, de-icing systems, safety precautions applied to de-icing systems, summary, conclusion, references, Appendix A, icing condition, Appendix B, BIDI testing, and Appendix C, distribution list. List of illustrations. List of tables. Executive summary. Introduction. Objective. Recently, research in the new aircraft ice protection technologies offer the possibility de-icing systems may be used with the aircraft turbine engine inlets that would otherwise equipped with the anti-icing system. Objectives of the project was to investigate de-icing technologies available that being developed to determine the effects of the de-icing systems of the engine. To evaluate the effects of the de-icing engine system of the engine study with the aim to, with one, determine the amount of inlet air accretes between de-icing cycles, two, identify analytical and or empirical method to determine the size and amount and path of ice shed during icing and inlet lip, and 3, determine the type of the engine inlet damage that can be caused by icing shed from the inlet. Background. Anti-icing system prevents icing from surfacing where de-icing system dislodge ice have been allowed to form. One possible advantage of the de-icing anti-system icing system potential with a reduced specific fuel consumption, SFC. To prevent formation of ice, anti-icing system must be continually operated by the icing conditioning. As a result, require the large energy output. Energy is derived with consuming fuel, thereby creating a significant specific fuel consumption penalty. Specific fuel consumption penalty is expected to be an event even more severe in next generation turbine engines, which, because of their high bypass design, will have decreased airflow to the core engine and in turn less hot compressor bled air available for heating aircraft surfaces. With the de-icing system, on the other hand, use much less energy because the system need not to be operated continually in icy conditions, but only at intervals just enough to keep icing from building up to be an intolerable level. The major concern when applying a de-icing system with the turbine engine inlet is the effect of the shed of the engine, with the shed of the ice, of the impact barrier of the engine components such as the fan blades, guide vanes, acoustical panels, etc. As secreted by the inlet surface between de-icing cycles may also come some of the airflow disruption, thereby aircrafting engine performance. These concerns are addressed and recommendations are made to minimize these effects. Some of the aircraft de-icing systems are equipped with particle separated to eliminate engine ignition on the ice shed from the inlet. This report addressing de-icing both without particle separators. Alright, de-icing technology status overview. This section provides a summary of the aircraft ice protection on comparing evaporative anti-icing, running wet anti-icing, and de-icing. In these detail with the current status of the aircraft de-icing technology, but the service of the aircraft with the developed material covered in this section was gathered in a survey questionnaire with the airframe engine ice detection de-icing system manufacturers. Respondents to the survey are listed in Table 2.1 and Table 2.2. Results relates to various types of ice protection to the engine which were used. The engine nacelle insulation, Figure 2.1, illustrates the relation between the four parts of the engine lip of the engine inlet duct, with the accretions can occur during the flight through icing conditions, and in order to avoid intolerable amounts of inlet ice buildup, Some type of ice protection is used. Completely evaporative anti-icing, causing water impinging in the engine inlet lip to evaporate, thereby preventing formation of the ice. Running wet anti-icing system not necessarily supply engine heat to cause the evaporation of all impingent water. We're able to keep water above the freezing point. In some of these systems, the water may run back into unheated regions and freeze there. So we have the inlet leading edge, the acoustic aligners, a compressor, your guide vanes, and fan. Schematic figure 2.1, schematic engine, nozzle installation, schematic illustration, spatial relationship between the inlet leading edge and ice acceleration can occur between the components of the engine inlet, might be subject to the damage from ice dislodged from the inlet leading edge. Table 2, respond to the de-icing technology status. Engine manufacturers like Avico, Lycoming and Textron, Pratt & Whitney, Rolls-Royce. Ice protection system currently used in aircrafts. In contrast to anti-icing systems, de-icing systems designed to remove the ice that allow it to accumulate in some level to pretend to be tolerable aircraft and engine. Therefore, de-icing expends much less energy than anti-icing because the system is activated only on a regular intervals. Ice buildup between the de-icing cycle at the time of the cycle's function on the particular system being used for icing conditions being faced. Anti-icing. Since the advent of the gas turbine, hot bled air from the engine, high-pressure compressors have been available for the heat source for the anti-icing engine inlets. This source can supply enough heat to prevent ice formation throughout most of the ice conditions. Large turbine engine nozzle installation. Table 2. There are three different systems of channeling directly, but directing hot anti-icing air over the backside of the engine inlet, leading the engine edge having the bill in figure 2.2. With a double wall system, air circulates through the duct and forms between the bulkhead and inner leading edge wall and flows from the holes of the inner wall to the outer heat of the outer wall of the inlet leading edge. So here we have 2.2 anti-icing channel system. From the top, the double wall system shows the inlet leading guide, a bulkhead, hot air inlet tube, inner wall and outer wall, double wall. The piccolo tube system B shows the piccolo tube, inlet leading edge and bulkhead. And then anti-icing channel system C, swirl system, anti-leading edge, bulkhead, and it shows the tube, a hot air inlet tube. Piccolo tube is in the system of the modification of double wall system, which for the inner leading edge of the wall is emitted with a high air circulation of the tube with the extent of the around the circumference of the inlet. Air exists from the holes in the tube of the heat, the inlet leading edge of the swirl system. Further simplification, which can be circumferential piccolo tube emitted so the hot air swirls around the circumference of the inlet leading edge entire space forward over the bulkhead. Figure 2.2c. Very few turboshaft engine installations such as turboprops use engine compressor air for the inlet anti-icing instead of the alternative heat source such as exhaust gas, hot engine oil, electrothermal heater, mats, or combination of the source used. Extreme ice conditions, some of the water may run back in the unheated regions. Inlet freeze there. The conditions are called running wet. Running wet systems use a low amount of energy compared to competitively evaporating anti-systems. This is the running wet system is preferred in engines and cannot be afforded to expend a lot of energy on ice protection. In extreme conditions, some of the water may run back to unheated engines and the inlet freezer there are an inlet and freeze air. That's called running wet. It shows the inlet leading in, inlet struts, hot air valve, hot fuel heaters from the scavenger pump, the oil tank, the oil cooler, and the hot air, oil, and electrical. Different shades. So black is total hot air. Oil is square pattern. Electrical hash pattern. Combination of hot air, oil, and electrical ice protection turbine installation. In some running wet systems, water channels are designed into the inlet surface to divert water overboard away from the engine. The type of the diversion keeps the water from collecting on the and freezing to the inlet leading edge. Not all running wet systems require water channels as designed. Some of the engines incorporate inlet air bypass ducts to channel a certain portion of the inlet away from the engine, and the bypass ducts can be modified as serve the particular separated with diverged foreign objects, such as birds icing away from the engine. These figure 2.4 show that these same bypass ducts can also help channel water away from the inlet leading edge. Show the propeller spinner, the actuator vanes 1 and 2, compressor and protective screen vane 2, air inlet vane 1, fixed vanes, and overboard. Position vane valves, air forming non-icing conditions, propeller actuator vanes 1 and 2, compressor, protective screen, vane 1, fixed vanes, air bypass channel, vane 2, protective screen. Turboprop and turbo particulars separated during ice conditions. Airflow with a diverted downward away from the engine, carrying heavier than air ice particles with it. In aircraft where running back in freezing unheated region of the inlet create the unacceptable risk and same energy sources of anti-icing, watering, and pigments areas. Such inlet leading edge can be used with the de-icing area further aft back where the water calculates and freezes. The protection technique is another way to reduce energy consumption compared to anti-icing all regions. Some propeller-driven aircraft still use a system consisting of air heated by exhaust manifold anti-icing. De-icing. Engine inlet de-icing system have been developed with the aircraft, which for the energy consumption must be kept to a minimum. The section described the de-icing system currently with the electrothermal mass and pneumatic boots. Those under development, the pneumatic impulse, the piezoelectric vibration, explosive with electromagnetic impulse, de-icing of the later electromagnetic de-icing, or BIDI appears most mature at this time due to the relatively high level of research and development associated with the research of the electromagnetic de-icing, in which Rohr and Rolls-Royce have participated extensively in the detail of Appendix B. For many de-icing applications, ice ingestion is not tolerable. Particular separators have become an integral part of the de-icing system. In those cases, if the particular separator does not use engine tolerance to the icing ingestions must be analyzed. Assurance of the ice ingestion does not adversely affect the safe engine operation. Related emerging technology improved the ice detectors. Anti-ice anticipated the advanced effect of the de-icing operation. Current research aimed developing ice sensor with the part of the automated ice detection de-icing actuator system. Pneumatic boots. Pneumatic boots are currently the most common mechanical system used for the de-icing, most widely means the wing de-icing for the general aviation aircraft. They are also used for the engine inlet de-icing and this level the turboprop commutator aircraft table 2.2. Pneumatic boot consists of an inflatable bladder bond of surface required for the protection. Figure 2 and 5 and then reference tube 1. During operation, pressurized air is forced into the bladder, causing it to expand. Surface deflection rate at approximately 0.35 inches a second. Expansion breaks the ice bladder bond, fractures accreted ice into small pieces to promote breaking off isolator bond. Ice adhesion reduction agent often applied with the bladder before each flight. Due to the deformation part of the wing aircraft inlet leading edge during the activated phase of the de-icing cycle, the pneumatic boots are limited. Though medium velocity applications up to half a Mach, pneumatic boots usually require a vacuum system to keep the bladder flat when not in use, thereby preventing irregular aerodynamic surfaces between the de-icing inflations. Alright, shows the skin engine inlet and the leading edge and the bladders. Schematic cross-section pneumatic boot de-icer installed with the engine inlet. As with any de-icing system, the minimum ice thickness at which the pneumatic boots become effective is 1/8 of an inch current with the pneumatic boots. But the ice must be continuous section of the pneumatic boots or the optimum effect of the ice thickness range of 1/8 to 1/4 of an inch. Most mechanical de-icing systems rime ice. Appendix A with the upper left airfoil with the inlet surface of the remain with the attached along with the leading edge of the ice. The RMIE ice accelerates slowly and can usually be shoved, but becomes excessively large and creates aerodynamic problems. Side of the fragments to be shed by the pneumatic boot, determined over the on and off cycle over the time and ice condition of the testing and previous expiration, and single with the egg engine, with their take with the utilization value of the new application. Many pneumatic boots are used with the conjunction with the internal particle separated with the minimum of the ingestion by the engine, and whether or not the particle separator is required depends on the icing damage challenge of the engine. Improvements made with the retarding erosion of the pneumatic boots have the result of a significant increase in intervals between boot replacement from 10,000 flight hours in the 1950s to 20,000 flight hours in the 1980s by many turboprop aircraft with a freezing point depressant fluids, or FPDs, of the conjunction of the pneumatic boot. De-icing can be applied externally with the propeller blades and wings, either with a manually during ground surfacing or in flight, transpiring with the freezing point depressant through the porous external surface of the in-flight with the transpiration of the freezing point. The depressant is not used without over the turboprop aircraft where the engine blood air is used to supply with the cabin air with the limitation of avoid the possibility accidentally contaminating bleed air off the air with a freezing point depressant, which could produce harmful vapors in the cabin. Electric heaters, electrothermal de-icing system are typically used with the aircraft with the hot air. Anti-icing system is not feasible with the hot air with a hot fluid system with an inherently slow thermal response from there may therefore be unstable for de-icing. Electronic resistant heaters, however, that can provide with a rapid heating method. The de-icing system can be timed so little that no runback occurs between heat periods. Electrical resistant heaters consist of the mat strip conductors embedded within the surface, requiring ice protection sandwiching over the mats between the layer of the neoprene and the glass cloth impregnated with epoxy resin. The mats are protected against water erosion, specifically polyurethane base coating the turboprop engine with the engine inlet leading edge and the propeller blades and propeller spinner. May use electrical heating with a protection. Electrical power is supplied by the generator to keep the size of the weight of the generator a minimum. De-icing electrical loads are cyclable between differential ice protected regions during operation of the de-icing system. Thin strip at the leading edge of the inlet continuously heated to prevent ice cap from forming on it or helping to mount with the ice forms of the areas further back in the mid and head. Cycle time electrical resistant de-icing system is adjusted with the schedule determined provided sufficient ice protection. Particular ice conditions encountered a two-speed cycle system is often. Alright, shows a glass cloth layer, inlet leading edge, electrical heater mats, consistently heated elements intermediately, electrical junction box, continuously heated elements, and intermediately heated elements, electrical resistant heating and engine inlet. Using short duration cycle, higher air temperatures, water with a concentration usually greater, long duration cycle with a low temperature range. Figure 2.7 the power timing with a de-icing cycle with a required with effective de-icing can be estimated based on the analytical method reference 2.2 with a comparison whether the provided de-icing system with the verification of the de-icing effectiveness check with the ice wind tunnel testing with electrical heater for the de-icing system, also with the conjunction with a foreign object bypass the duct with to prevent shed ice from being ingested into the engine. The pneumatic impulse with the modification pneumatic boots and the pneumatic impulse with the de-icing system currently or the development system work essentially with the area same with the pneumatic boot system, however, instead of expanding slowly, inflatable bladders are expanded rapidly with a high pressure pulse for the air with a surface of the movement of approximately a tenth of an inch and within a tenth of a second. Because the shortened times of the bladder inflation, the minimum deflection, deformation, airfoil surface of the system can be operated with a higher speed aircraft with pneumatic boots. These systems currently being developed with a titanium sheath that containing with a flexible boot and enhancing durability, so reducing erosion. Electromagnetic impulse de-icing. Electromagnetic impulse de-icing, it requires no external addition of aircraft skin. Electrical current pulse generated with the capacitor transmitted through the spirally wound flattened coils made from ribbon wire. These coils are rigidly supported with the inside of the aircraft skin, but are separated from it by a gap approximately a tenth of an inch. Various cooling mounting configurations are described in Appendix B. 2/7 show the decycling external resistance heater, show the maximum and the minute current and 0 to max and 0 to max. First you have your fast cycling speed. In one cycle you have an engine inlet, as prop and spinner, and air engine inlet. On the bottom we show a slow cycling speed, one cycle, engine inlet, propeller, spanner, and engine inlet. The time is much greater. Alright, this shows 2H of the cross section through the inlet edge of the bulkheaded mounted EIDI coil doubler, foam fiberglass bulkhead. Alright, your BID coil current produces a magnetic field with induced the eddy current into the thin metal skin. Figure 2.9. Two current fields repel each other, and the resultant force causes the loaded displacement high acceleration movement of 1,000th of an inch per 1,000th of a second of the skin adjacent to the coil. The movement shatters the ice and breaks the bond between the ice and the skin. The ice is then swept away with the strip of the aerodynamic force for the crack debond dislodge process usually requires the two impulse separated by the recharge time of the capacitor of typically 3 to 4 seconds. Power supply is then electrically switched to the coil or coils to another location of the engine inlet process that is repeated the system cycle with back to original coils before the apparently appreciably amount of ice is secreted. Connecting wires from the capacitor of the EID coil must be in low resistance inductance to achieve the fastest impulse response. Inlet skin thickness is less than the minimum required for the adequate conductance of the inducing eddy currents and metallic doublers used to increase the inductance. In Figure 2A, the doublers are usually aluminum disc slightly larger than the coils bounded with the skin between the skin and the coil. Metallic doublers are necessary with the non-metallic composite skins. The energy required for the electromagnetic impulse de-icing any area is about 1% of that required for the thermal anti-icing equivalent area. To achieve the electromagnetic impulse de-icing design must be carefully electrical pulse with the electrical structural response to the leading edge. This design procedure is summarized in reference 2.3, explained in detail in reference 2.4. Your electromagnetic impulse de-icing currently is under development and being considered for some of the new engine icing protection designs. Tests as far performed have been demonstrated the electro impulse de-icing system is an effective de-icing system. This test the results are summarized in Appendix B. It shows cross section of the electromagnetic impulse de-icing system coil showing coil's current magnetic field with the resulting eddy current in the skin, currents flowing in the loop out over the paper plane since dotted and positive. This is magnetic field, eddy current, skin, and the coil. Electromagnetic expulsion. Another de-icing system not been tested with the electromagnetic expulsive de-icing system boot bonded to the inlet surface of the boot consists of the elastrometer polyurethane material. Thickness of 0.02 of an inch, using a U-shaped ribbon conductors embedded with a parallel to the boot surface of Figure 210 with a large content of the port power storage unit is released for the conductor, creating opposing magnetic fields in the adjacent area of the U-shaped conductor. Figure 211. Magnetic force field caused by the conductor separately expulsively forcing upward of the expanders of surface of the boot and separate with the lower fixed surface of the aircraft. The boot defects 0.09 of an inch of the 200 microseconds, creating a G-force and with a range of 700 to 1500 Gs. Elastic properties of the boot and quickly collapsing back with a thin layer of the boot. Short deflection time makes the system applicable throughout the subsonic, transonic ranges and possible into supersonic range. Energy requiring 750 to 1500 joules with a ranging from 1000 to 2000 volts, which is effective at removing ice accretions and thickness of the 2000s to 1 inch. The material from which the boot is made currently is used on several naval aircraft, including the FA-18 in reference to 6, for added protection against the rain erosion. From an experience, it has been possible to estimate that the lifetime of the boots is 10 plus years. The particular benefit of the de-icing system is that they applied externally, therefore easily retrofitted on existing aircraft. Figure 210 shows the electromagnetic expulsive de-icing system boot shown in the expanded state that you have the conductors of the fixed surface of the boot attached to the aircraft, the expandable surface of the boot. And then it shows the 211 arrangement ribbon and conductor electromagnetic expulsive de-icing boot direction of the current flow in the indicated arrows. Helicopters. Most helicopters don't have a removal system with the effect throughout the FAR envelope with the icing conditions. At this time, no U.S. manufactured civilian helicopters were certified for flight in icing conditions. However, the electrothermally heated rotor in conjunction with the ice rating sensitive permit for the operation of some military helicopters in light icing conditions, providing protection limited set of the icing conditions, along with the information helps with the helicopter pilot shows the duration safe flight. For helicopter duration flight, ice condition is limited to the icing hub of the rotor blades. Therefore, a good portion of icing research focused on rotor and hub, rather than on the engine and ice protection. Severe limitation of helicopter flights for the ice conditions have been the driving force behind current efforts to develop the new icing protection technology, such as phobic coatings, mechanical vibrators, microwave emitters, electromagnetic impulse de-icing systems, pneumatic impulse systems. That technologies in some cases may adapt the fixed-wing aircraft as well. Method of the engine inlet ice protection, unique helicopters extremely mounted heated inlet screen. Electrical resistance heating of the screen keeps large ice acceleration from forming, therefore allowing very small ice fragments resulting from water to pass into the engine inlet. The small ice fragments are further the removal of the internal particles separated with this system. Typically are not intended for long duration operation, heavy ice conditions. On the other means, helicopter ice protection now used in electrothermal mats and experimental pneumatic boots for rotor systems. Reference 2.7. Ice detection systems in aircraft without ice detector aircrews are alerted to the ice conditions, either the weather advisory by seeing ice accumulations in the aircraft. The ice detectors currently use the production aircraft table 2.3 indicated when ice is forming on which surface of the new ice detectors are also being developed to measure ice accretion on the rates and thicknesses. Such information will use the aircraft crew or by automatic electronic control to adjust the de-icing operation, icing conditions encountered, and improve the efficiency of the de-icing systems. The other improvements that have been developed improve the reliability, self-testing, experimental, further change role of ice detector supervisor for the controlling by ice conditions. And frequently with the most commercial aircraft, the ice detection system must be highly reliable, able to function following the long inactive periods, but this suggests the need of the continuous self-testing will be easily achievable with modern electronics. Most icing detectors classified in 4 categories based on how they measured accreted ice: vibrational, electrothermal, pulse, echo, and optical. Vibration. There are 3 types of ice detectors chained with the vibration to sense ice. One system of vibration razor blade type of the probe extends from the surface of the aircraft into the airstream. The ice accretes on the blades. Figure 2.3 show the Army equipped with the anti-inlet icing detection system all have vibrational temperature type sensors. The mass of the probe is altered with a resonant frequency change with the correspondingly frequently changed in the sending electronically transmitted cockpit display. Second type of the vibration device is a coin-shaped piezoelectric diaphragm mounted flush on the surface of the aircraft, and it accretes on the diaphragm, and the stiffness increase with proportional to the thickness of the ice, causing the diaphragm natural oscillation frequency increase sharply. Frequency change is measured with additional electronics, and the piezoelectric system is available in a probe configuration. Third type of the vibration device currently used in the development consists of the piezoelectric film bound to the inside of the structure, such as the inlet. Figure 2.13. A broadband vibration frequency is applied to the structure, elicited with a natural resonance, and then created the ice change to the structures. Resonant frequency chain with a transmit with a microprocessor, the input of the ice thickness system is then part of the autonomous ice detection removal system ability to activate the de-icing process for the predetermined ice thickness is reached. Or it shows a piezoelectric diaphragm, a leading edge of piezoelectric diaphragms in the size of a quarter. Electrothermal type of the test detector operators sensing change of the electrothermal character of the detectors. The ice accretes. This detector cylindrical probes extending to the airstream with a nickel wire wound around the probe. Either pulse of the continually sent with the root of the wire when the ice accelerated with the probe. The heat generated with the wire by the electrical pulse absorbed by the ice. The heat change of the wire is monitored electronically. So here it shows a test support jig, a stiffener spar, an impulse generator, an aircraft surface being de-iced, and piezoelectric film icing detection de-icing system general arrangement. Reference arrows follows on the 2 schematic views relating to one another. So this piezoelectric film and the square triangle is the impulse generator, and the aircraft surface being deloaded. Pulse echo, ultrasonic pulse echo icing detectors are being developed to operate measuring with the return rate of the acoustic signal reflected by the layer of the accreted ice in figure 2.14. Ultrasonic acoustic waves from the transmitter picked up with the receiver that, after being reflected by the ice layer of the aircraft surface during the transmission of the waves that reflected back and forth between the two surfaces of the ice layer. Multiple reflection echoes required for the sound bypass acoustic block placed on the transmitter with the receiver to prevent disimpingement of the swing signal from the transmitter on the receiver at the time when the required for the sound on the travel from the transmitter to the receiver, and directly related thickness of the ice layer, in addition to the measuring of the thickness of the ice ranging from 5,000 to 300,000 of the inch in the system capable of the measuring of the rate ice acceleration. Ultrasonic detectors may be countered to fit flush with the leading edge surface, thus conforming the aerodynamics of the aircraft. Figure 214 shows an ultrasonic pulse echo system detector concept that transmitter acoustic waves and the receiver going through an ice layer of 5,000 to 30,000 of an inch, 5,000 or 300 5,003 of an inch of the multiple echo required ice layer sound on the cross acoustic back called acoustic block. Optical ice detector suit with a special requirements of helicopter during, however, the low speed flight. Ice detector required with the forward velocity may fail to indicate icing, although airflow into the engine and icing is high. One company has developed an ice detector and an ice acceleration rate center small suction device to induce the airflow through the tube with the routed mounted across the diameter of the airflow through the tube with its set with to simulate with the airflow with the engine inlet with the light shines across the front with the rod of the line and with the optical fibers. Ice from the forms on the rod that occludes with the light when the rate of shadowing on the elliptical fibers yield with the icing rate. Periodically, electrical heating of the rods recycle with the measuring system and the forward speed when it becomes excessive. However, the accuracy of the instrument deteriorates. Several other types of icing detection systems identified with the survey and in literature search. However, the detail of the information was restricted primarily for the proprietary reasons. Alright, ice acceleration, and ice accretion and de-icing evaluation. Cut the tape there.